Let's talk about something that happens every single time you charge your phone, drive an electric car, or use pretty much any modern electronic device. There's a silent, invisible process going on, converting electricity from one form to another. The thing is, this process has never been perfect. Today, we're going to dive into the hidden world of power electronics and the relentless quest for 100% efficiency. It's a story that involves a new wonder material and some seriously smart thinking.
All right, so here's how we're going to break this down. First, we'll look at the fundamental problem with the tech we use right now. Then, we'll introduce the hero material that's changing the game. After that, we'll see how engineers figured out how to tame its incredible power. And finally, we'll look at the mind-blowing performance they managed to unlock.
Okay, first things first. Our entire digital world is built on electricity. But there's a huge, invisible leak in the system, one that engineers have been trying to plug for decades. Seriously, think about it. That power adapter for your laptop, the charger for your phone, the complex systems in an EV, they all have to convert power to be useful. But some of that energy just vanishes. Where does it actually go?
And the answer is heat. At the heart of every one of these devices is a tiny electronic switch, flipping on and off millions, sometimes billions of times per second. For decades, the go-to material for these switches has been good old silicon. But every single time it flips, it creates a tiny puff of waste heat. And when you add all those puffs up, it becomes a huge source of wasted energy.
Look, silicon has been amazing, but it's hitting a wall. It's reached its physical limits. So to take that next leap in efficiency, we need something better. And that's where our new hero comes in. Silicon carbide, or as everyone calls it, SiC.
So let's put these two head to head. You can see right away, SiC is just in another league. It has way lower electrical resistance, which means less energy is just burned off as heat. It can also switch faster and handle much higher temperatures without breaking a sweat. Basically, in every way that matters for a power switch, SiC isn't just a little better, it's fundamentally superior.
So what does this actually mean for you and me? Well, because these SiC switches are so much faster and more efficient, we can build power converters that are smaller, lighter, and waste a lot less power. This is an absolute game changer for things like electric vehicles, where it can boost range, and for the power grid, where it helps us use renewable energy more effectively.
Okay, so we've got this incredible new material. Problem solved, right? Well, not so fast. SiC is so good and so fast that it creates a brand new problem. It's incredibly hard to predict what it's going to do. The old rulebooks that were written for silicon, you can pretty much throw them out the window.
This is the exact question that was giving engineers headaches. If you can't accurately model how the switch behaves from one nanosecond to the next, you can't really design an efficient or safe system around it. You're basically flying blind, guessing at energy losses and hoping you don't get a random voltage spike that blows everything up.
The solution, and it really was a breakthrough, is something called the Mechanism Segmentation Transient Model, or MST. Instead of just treating the switch flip as a single event, this model acts like a super slow-motion camera. It breaks down that nanosecond-fast process into tiny, distinct physical stages, letting us see what's really going on under the hood.
And here's what that slow-motion replay looks like. You can see it's not just an instant flip. It's this complex little dance. First, a capacitance has to charge up. Then the current starts to rise. The voltage begins to fall. You even get this little current overshoot before everything finally settles down. By modeling each of these physical steps, engineers can finally predict exactly what's happening and when.
All right, so now we have a super fast switch, and we finally have a model that can understand it. So now what do we do with it? A switch by itself is just a switch. You have to put it into a larger system to do something useful.
And that system is very often the dual active bridge converter, or DAB. The best way to think of this thing is as a universal translator for electricity. It uses two sets of switches to move power back and forth across a transformer. This allows it to seamlessly and efficiently connect two different power sources, like the high-voltage battery in an EV and the lower-voltage system that runs the motor.
Okay, let's take stock. We've got the perfect material, SiC. We've got the perfect system to put it in, the DAB converter. We should be good to go, right? Well, almost. There's one last, absolutely critical piece to this puzzle.
To get every last drop of performance, you need the smartest control strategy possible.
For a long time, the old way of controlling these converters was pretty basic. It's called simple phase shift, and while it works, it gets really inefficient as soon as conditions aren't perfect. The new advanced approach, called universal phase shift, or UPS, is so much smarter. It has way more knobs to turn, so to speak, which lets it constantly adapt and hunt for the most efficient way to run, no matter what's happening.
So how does this smart control actually find that peak performance? Well, it's on a constant three-step quest. First, its top priority is to make sure the switches turn on when there's zero voltage across them. That eliminates a huge source of waste right there. Second, it fine-tunes all its knobs to make sure the absolute minimum amount of current is flowing to get the job done. And finally, the genius part is it pre-calculates all of these perfect settings and stores them in a lookup table so it can make the perfect choice in a fraction of a second.
And the results? They honestly speak for themselves. This chart shows a really tough, real-world scenario where the voltages don't match up well. The old, simple control method just falls apart. It's only about 70% efficient. Other advanced methods do better, sure, but the fully optimized UPS strategy just crushes it, hitting nearly 91% efficiency. That's a huge difference.
In fact, let's just put a single number on that improvement. In the absolute toughest conditions they tested, this new UPS strategy gave a, get this, 20.49 percentage point increase in efficiency. In the world of power electronics, getting a single extra percent is a massive win. A 20% jump? That isn't an improvement, it's a revolution. It turns a ton of wasted heat back into useful power.
I know. We have gone deep into some serious engineering territory here. But trust me, the results of this quest for perfect efficiency, they have huge implications for every single one of us. So let's just boil this whole story down, right? It's a three-part victory. It all started with a superior material, silicon carbide. That material's potential was then understood using smarter models like MST. And finally, all that potential was unlocked with advanced control strategies like UPS. And the result is simple. Less wasted energy means more performance for everything. You don't just have to take my word for it. The researchers who developed this new control strategy put it perfectly. They said it has superior optimization effects and that it substantially improves the system efficiency. That's about as clear a declaration of victory as you can get in a scientific paper.
And this is the bottom line. This is why it all matters. Every single percentage point of efficiency that we gain means an electric car can drive farther on one charge. It means we waste less precious energy bringing power from a wind farm into the grid. And it means the power brick for your laptop can get even smaller and lighter without getting scorching hot. This is engineering that directly improves our lives. So that leaves us with one final fascinating thought. For decades, this kind of near-perfect efficiency was just a theoretical dream. Now, it's a reality. So what's next? What technologies that were once held back by the bottleneck of power conversion can now finally be built? What impossible things are about to become our new reality? That's something to think about. Thanks for joining.